Okay, so maybe we should begin.
Do you want to go ahead and introduce it?
Oh, yes, I will introduce, sure. Ready? All right, yeah. Welcome, everyone. We have our speaker today, Dr. Vishal Gajjar from University of California, Berkeley and SETI Institute. Vishal is a staff astronomer at SETI and visiting scientist at Berkeley. Vishal did his PhD from Tata Institute of Fundamental Research, TAFR in India. It's one of the most premier institutes in India. And then he came over here, a couple of postdoc stints. Then he was a Templeton Fellow at some point, postdoctoral fellow, and then moved to Berkeley as a staff astronomer. Vishal works on SETI related, radio SETI related aspects, fast radio bursts, and also on pulsar astronomy. And so if you're interested in any of these topics, please contact Vishal or contact me and I'll put you in touch with Vishal. So there are some interesting projects Vishal is working on, and I think he will cover this in his talk. And this is SETI related talk, so I thought a lot of people would be interested in this. So Vishal, please go ahead and let's start it.
Yeah, I hope everyone can hear me okay. This is going to be sort of very informal talk, so if you have questions, feel free to kind of, post it in chat, and I think Joe can kind of convey that to me. So first, I'd like to thank Ravi for hosting me here. It's been great. I have been here for the last couple of days, and I thoroughly enjoyed my visit, and we had a great sort of discussion on potential of doing some techno-signature activities involving people here. So this has been great. So as Ravi mentioned, I work on various topics at SETI Institute and Berkeley. But today I'm going to mainly focus on our work in techno-signature. So let me define what exactly I'm going to talk about. So I mean, we are all kind of interested as an astronomer into this question, like, are we truly alone in the universe? And over the years, we have learned quite a bit about our place in the cosmos. We have found, I'm giving this seminar in the exoplanet series, so I don't really need to define or kind of justify the prevalence of extrasolar planets, right? We are finding them almost everywhere. Like we are finding them in habitable zone. Like Ravi did a great work on sort of defining what exactly is a habitable zone, and we are finding planets, for example, in these zones. So the question whether Earth is sort of very uniquely located is no longer there. I think there are lots of planets which are ideally located. Astrobiology, on the other hand, is also teaching us quite a lot about life itself, like how life can survive in extreme condition. And that both of this basically suggest one thing, that probably we are not alone. So how do we answer this question? So we have two ways of doing it, which are essentially same. If you have life, you can find some signature of life. How do you find signature of life? Like what we call biosignature is an evidence of biological activity as we know it. So we have a certain definition of life. We know that what life does, and like when life is there, it produces certain byproduct, which we now have a capability with, for example, with JWST and the future World Observatory, we will probably potentially be able to identify biosignatures. There are some limitations still, even in the next couple of decades. We will be limited in terms of our capacity to how far we will be able to detect biosignatures. So unless there is life right in our neighborhood, the chance of us detecting it in the immediate future is still a little bit far out. Technosignature, on the other hand, is an extension of biosignature. So if you have life, it is also possible for life to evolve and become technologically more advanced. So the question is that, can we find evidence of technology? There are lots of work that has been done into this, and obviously I will not go into the details of every bit of technosignature, but I'll give you a bit of some flavor of what exactly I mean when I say technosignature. So let me define this term technosignature. So technosignature is a direct or indirect evidence of past or present technology developed by extraterrestrial life. And you can basically put a lot of things under the same umbrella. I'll start with, for example, things in our own solar system. If this was a Oumuamua interstellar visitor that kind of we detected a couple of years ago, we probably have a proper definition. I don't work in this field, so maybe you have other expert in the area who might have better the justification for it, but for some time, this was a mystery, like we didn't understand what it is. So people also speculated that it is possible it is some kind of like a Bracewell probe. So similar artifacts are possible to search in our solar system. The most interesting aspect, which I can also talk a little bit about, are the exo-engineering projects. So like if advanced civilization is sort of harnessing energy of their parent star, okay, we can also see evidence of it. We can see some kind of like a excess radiation or heat excess that can escape from the system, which are possible for us to detect. City light are also a pretty good example. Like if you have a planet which artificial lighting on it, so then that is also possible. At least up to certain distance for us to detect it. You'll see certain different albedo on that, and you will have a chance of detecting it. Obviously, limits are there only for within a solar neighborhood. Atmospheric pollutant, which Ravi also is an expert. I mean, he would be able to kind of talk more about it. Like the way we are trying to detect biosignature by taking spectra of extrasolar planets, we are trying to we can also kind of extend that to detect artificial molecules, so molecules that don't necessarily exist naturally, and you can try and kind of, search for them. We do have a way of currently searching for them. So those are another examples of potential technosignature. But I will, for the remainder of the talk, will only focus on the electromagnetic waves. Electromagnetic waves through which we can detect evidence of direct or indirect evidence of technology. So this is just an outline of rest of my talk. So how are we searching for different kinds of technosignature in the electromagnetic spectrum? I'll mainly try and focus on three main aspects because it's difficult for me to give you everything that is happening in this field, but I can try to give you at least the three main area. Like what exactly are the different kinds of electromagnetic signals that we are searching for in this field? How are we searching for them? What are the challenges that we face when we go and search for these signals? How AI and ML is basically helping us overcome these challenges, and then how future upcoming facilities which have slightly better sensitivity will be able to push this limit to search different varieties of electromagnetic waves. So at the end of the talk, if you are able to get answer to these three questions, like what are we searching for, how are we searching, how AI, for example, is helping, and how are we pushing the boundaries, I would consider this as a success. So let me take a step back before I jump into what we are doing right now. I also like to take this moment to give you an outline of what exactly has been happening in the field for the last several years. So it's not a new idea. Searching for technology from extraterrestrial life has been there since many, many decades. In fact, in 1960, Frank Drake, in fact, conducted the first experiment to search for extraterrestrial civilization at radio frequencies, and this was called Project Ozma, and he basically used this NRO dish. In 1970, in fact, from 1970s and 80s, NASA was also quite interested in funding SETI efforts. But in 1993, in fact, in 1992, NASA funded a very large-scale SETI program called the High Resolution Microwave Survey. But a year later, this was scrapped. So NASA kind of cut the funding for conducting more technosignature searches since 1993. And it's been the case ever since that NASA has not really formally funded radio technosignature searches. But SETI still thrived because we were able to get attention of several private donors. So in 1994, SETI Institute was formed, which is where I am based at. In 1999, at UC Berkeley, there was this program, there was this project which was launched, supported to NSF, SETI at Home. I guess many of you who have probably downloaded the screensaver for SETI at Home, and you must have used SETI at Home to help us analyze the data. So my first postdoc when I joined the group, I was working with the same team who designed the SETI at Home. So SETI at Home was a pretty famous and successful project. So SETI kind of pushed the boundaries of conducting searches through private funds. In 2007, SETI also got some funding from Paul Allen, who was a co-founder of Microsoft. And based on that, In fact, Jill Tarter, who started the SETI Institute, was also the main key person to basically initiate this telescope, where I also currently reside, is the Allen Telescope Array in Northern California. But the major step came in 2015 in terms of funding, and also that came through a private funding. So we had a private donor, Yuri Milner, who came on board, and he basically started this program called Breakthrough Initiative. And he decided to fund 4 or 5 different programs. One of them was Breakthrough Listen, and each one was awarded something around $100 million. And in fact, this was all late Stephen Hawking and Frank and others were also participating in this endeavor as well. So currently, I'm also part of the Breakthrough Listen. I'm a project scientist with the Breakthrough Listen. This program started at Berkeley, but now we have moved our headquarters to University of Oxford. Very recently, just a couple of years ago, we also got a huge amount of funding from another private donor. This was Franklin Antonio, who was a co-founder of Qualcomm, who basically left us close to around $200 million for continuing the search. So although government funding has been limited in this field, we've been very successful in getting private funding, and to some extent, we are currently, I can say that the SETI is sort of permanent funding. So we will be able to continue the searches that we are trying to do. So just as a sort of a good news that even if the private sort of the government funding dries out, there are potential avenues. One is what is possible to explore from private sectors as well. All right. So that's just the history of how SETI has been able to acquire funding, and I hope that it sort of gives you some idea of where we get the money to work on all of these things that I'm going to talk about throughout the rest of my talk. So what are the different kinds of technosignatures? Let me come back to science, and let me talk about what are the different kinds of technosignature we try to search in the electromagnetic spectrum. One of the classical examples of the electromagnetic spectrum we try to search is that signal that is focused only in a certain frequency range. These are what we call narrowband signal. We know that nature produces lot of signals of various varieties, but it does not produce signal that is extremely narrow in frequency. So, we produce them quite a lot. So if you study the radio spectrum from human, we see that there are a huge amount of signal that are narrowband. And all of these are because they are what we call carrier waves. So people who do communication, they know that when you try and send signal with modulation, you try and also send a carrier wave. So it can be a way by which we can basically communicate or transmit information across large distances. So carrier wave or narrowband signal could be a potential signal. And second, in fact, Coker and Morrison suggested that this is something that is very simple for anybody to do. So if there is a potential civilization out there, it's not an advanced technology. You don't need necessarily an advanced technology to create a signal like that. So it is very easy to generate, and it can travel very far. The other class of signal are in optical domain, are nanosecond duration optical pulses. Again, something that we don't know nature to produce. And in fact, this was proposed by Charlie Towne, who won a Nobel Prize for discovering laser. And he wrote this paper in 1961 that even the optical pulses can be used for long communication with extraterrestrial civilization. So these are two main prime examples of electromagnetic signals. There are also other signals which we try and search. I will not go into too much of the details for the lack of time, but just to give an idea, there are a whole range of different categories of electromagnetic signal that we try and search, like signals that are broadband, exhibiting some weird artifacts, signals that are narrowband but pulsating. We also look at different stellar type of different exoplanets and look at their transit light curves. If the transit light curve shows any odd dips or any non-periodic structure, those are also interesting for us. I will come to that in a later part of my talk, so I'll skip that for now. All right, so I hope that just gives you some flavor of what exactly we are trying to search. So how are we searching, and where exactly are we searching for all this, right? Like, I mean, that's the big question. So we search for all of these different categories of signal across wide variety of objects. Obviously, we cannot search everything at the same time. We have a limiting capacity in terms of resources, instrument that we use, and all that. So we have created a certain data set, a database of where exactly we want to search. So what we are trying to do is that we are trying to search at least our solar neighborhood, because that's where we have the maximum sensitivity. This is where you will be able to detect the largest, if signal exists, your chance of detecting in your neighborhood is the highest. So we have created a database based on the Gaia catalog, a nearest 1 million star sample, and we are conducting a deep searches on them. We also don't need to be limited in terms of only looking at stars, because who knows, technology might not even be associated with a star. It could be a free floating object that is producing some signal. So we are also searching the entire galactic plane and the galactic center. I'll come to that in a minute, the galactic center part. We are in fact also searching extragalactic objects. So we have a sample of 100 nearby galaxy. You might argue that our chance of detecting a sort of intelligent life in extragalactic object might be extremely low, but you never know. The beacons could be bright enough, and you can still possible to detect even if they are in a different galaxy. The most interesting part is that we are looking at exotic objects. So these are the objects that defy our current understanding of astrophysics. Now, obviously, most of them, 99% of them, might have some astrophysical or must be have astrophysical origin, but we are still kind of following them up in a hope that maybe one of them could be potential target, and we don't want to miss them. So anything that we see in literature or any research, any publication that comes out arguing that they are not able to understand this particular phenomena, there is a weird object out there, we try to follow it up as well. One of the things that I closely work on is the Galactic Center. So I'm a project scientist for surveying the Galactic Center as a part of the Breakthrough Listen program, and we are conducting 600-hour survey of the Galactic Center starting from 1 to 100 gigahertz. Now, the idea is that why galactic center? So first of all, if you look towards the galactic center, you have a highest number density of star compared to any different direction in the sky. So if you look towards that particular part of the sky, you have a highest chance of seeing large number of stars. So you have a high chance of detecting. In fact, there are theoretical modeling people have done in terms of propensity of finding life or propensity of finding like habitable planets around it. And if you see the plot at the bottom on the left-hand side, this is from one of my paper, where we actually model this, and we found that as you go closer to the galactic center, now I'm not talking about exactly the galactic center. We know that the galactic center region is highly chaotic, but if you go slightly closer to that, you will see a high number density of star, and just the number of star itself is so large that you have a high chance of finding fraction of star with habitable planet just going to go high. So this is argue that if you look towards that direction, you have a high chance of detection. And what are we using basically? Which telescope are we using to search for this? And the answer is almost everything. So Breakthrough Listen program, because we have been funded quite well, we've been successfully able to collaborate and able to basically get time. We also write proposals. We have students and we have faculties who work with us. So we basically work in a very large collaboration. And this is a question that I guess many people are interested in, but they just don't know how to get access to data. So the another thing we're trying to do is that we collect data and we conduct these observations of all the target that I just mentioned from whole range of facilities that you are seeing right now. And we make all the data public. So we have an online data portal where you can go and download data which we have collected from many of these telescopes that are currently online. You can do your own searches. If you have certain ideas about certain classes of signal, you can go ahead and search for them. So I will not have time to go about discussing, because each program is quite unique and quite exciting, but obviously I'll focus on just a couple of them, like how we are conducting techno-signature searches on just a couple of them. So let me take the entire electromagnetic spectrum. Like this is what we are doing. We are trying to answer this question, how we can find techno-signature in the electromagnetic spectrum. So this is the electromagnetic spectrum. Let's start with there are no active programs, unfortunately, at X-rays and gamma rays. So we start with the optical band. In the optical band, we have a program that is running at the Veritas telescope. This is a 12-meter class 4 mirror. The primary purpose of this is to detect cosmic rays and high energy gamma ray hitting the upper atmosphere. So the animation on the right-hand side, what it shows is that when these charged particles basically, or when these gamma rays enter the upper atmosphere, it creates this Cherenkov shower. And you have multiple mirrors on the ground. So basically this interaction happens very high, up to like 15, 20 kilometers. And then on the ground, you basically have this Cherenkov shower photon reaching to you, which you are able to detect it. So the best thing about that instrument is that it has the capacity to detect photons at very high speed. So it is able to detect up to 3 nanosecond pulses, which is great, which is exactly what we are trying to search. If you remember earlier, we mentioned about this idea about potential technosignature is the nanosecond duration optical pulses. So we use the same telescope, but the argument is slightly different. So here I'm showing you a plot, and there are two images. On the left-hand side is the image of a cosmic ray or a gamma ray hitting the upper atmosphere, creating this Cherenkov radiation, and then they are being detected by multiple sites. And you can see the CCD images of both these mirror, and you can see that they are not at the image of the photon that is being received is not at the same location if the origin of this photon is the upper atmosphere. But if the origin of the photon is a plane wave that's coming from far away, then in the CCD image, they will appear at the same location. So we can use this strategy to detect nanosecond duration pulses that might be coming from far away. Okay, the another thing which I personally am very much excited about, although I'm a radio astronomer, but I collaborate with a lot of people to work, and we try to basically look at light curves of transit, various transit, and we try to understand that is it possible for us to model non-spherical shape transit? So we have actually created a CNN-based classifier, and we have used that classifier to train. Basically, we have trained the classifier on various different shapes that are transiting in front of a light, transiting in front of a star. So what you see on the left-hand plot are the examples of 3 different shapes like red, blue, and green. And at the bottom, you can see the transit shape that will come out of this different shape. And as you can see, they are similar, but there are subtle differences between all 3 of them. So you can see, you can use this and you can train a CNN model to identify different kinds of transit light curves. So the idea is that if you have a non-spherical object that is passing in front of the disk of the star, for example, a potential Dyson sphere or Dyson sphere in the making, you would have you will have a chance of detecting it. And in fact, we will be using data from Kepler and TESS, which has made all the data public. And in fact, I was talking with Ravi as well, and like we are very excited to also collaborate with Roman when it goes online, and when we'll be able to use the data as well for that. In fact, for people in the audience, if any of you have students or if you are a student looking for a postdoc, we are hiring right now exactly for this purpose. And this was just a press release came out yesterday. There was a private donor who is interested in this question. So he gave us funding to hire a postdoc. So we are actually hiring a postdoc working at the SETI Institute to work exactly on the problem that I just discussed. So if you're interested, reach out to me. All right, so let's move from the optical band to the radio band, which is where I work on. This is basically what I do on a day-to-day basis. Radio have a lot of challenges because radio telescope basically sees almost everything. So this is just an obviously AI generated image of a radio telescope. Obviously, nobody would like to put a radio telescope in a location like this, but the idea is that almost everything around us produce radio waves. You have satellites, you have drones, mobile phone towers, all of these produce radio waves. So when we try to detect radio waves from like extraterrestrial light, this is a challenge for us. Like, how do you disentangle what is truly coming from a sky versus what is generated by our own technology? So we use various different strategies. So I'm now coming to the point about like, okay, what are the challenges that we face in terms of disentangling what exactly is originated by extraterrestrial life versus what is produced by anthropogenic sources? So let's see, the strategy that we use are different for different telescopes. So let's say if you have a telescope that is like a one giant big radio telescope. This is the telescope which we known as the Green Bank radio telescope. It's quite big, it's 100 meters in diameter. So the way we use it is that we point it towards a star, and then we basically point it away from the star, and we do this multiple times. Radio telescope are quite sensitive towards one particular part of the sky, but they also have sensitivity almost everywhere. That is the problem, right? Because even if you are looking in that part of the sky towards a star, your interference could be located right next to you, even if your telescope is not looking there, but you're still getting the signal into your data, although with a slightly reduced sensitivity. But you can use that to basically eliminate things that are local, because if you look away from the star, if the signal was truly coming from the star, it should disappear. And if the signal is coming from a local sources, it will still remain there. So we do this strategy to basically eliminate false positive. And like these are two worst, some of the largest radio telescope that we use. One, this is in Green Bank Radio in West Virginia, quite close to here. And then second is the Sardinia radio telescope in Italy. And as you can see, both of them gives us a quite high frequency coverage. Like we use Green Bank to go all the way to 100 gigahertz, and SRT we use up to go to 26 gigahertz. Going from extreme high frequency to slightly mid frequencies, like something around 1.4 gigahertz, we use these other radio telescopes. Like one, it is located in China called FAST. So I also closely work with the team in China. FAST is sort of like a next version of Arecibo. Similar to Arecibo, it is designed in a valley, but it is bigger than Arecibo. It's actually 500 meters in diameter. And it has excellent sensitivity. The best thing about it is that it has a 19 beam receiver, which means that we no longer have to do on and off. The 19 beam receiver allows us to look at 19 different parts of the sky at the same time. So what you can do is that you can basically search all the 19 beams, and that way you can disentangle what exactly is coming from, terrestrial sources versus what is actually skybound. And that way you can basically get rid of interferences that we normally see in our radio searches. The other technique is using an interferometer. So there are a number of interferometers. We have three main interferometers. One is the Very Large Array in New Mexico. Second is the MeerKAT array in South Africa, and then the Allen telescope array, of course, that I mentioned earlier. And all of the radio telescope, we use the same strategy. What we do is that we form multiple beams. So multiple beams are formed digitally. It is exactly similar to like pointing your telescope to a different part of the sky. So what you can do is that you can take the data from all of these different antennas, and you can combine digitally them in a different ways, which forms the beams in the different parts of the sky digitally. And then you can basically, again, do the same thing. You can search them and think of them as an independent beams, and search all of them independently. If you see the same signal in all the beams, that means this is produced by terrestrial sources. If you see a signal that is only there in one beam, that's interesting for us. So that's where we can disentangle what is terrestrial versus what basically is coming from the skybound sources. Going back to even lower frequencies, we even search for radio technosignature to very low frequencies of 10 to 30 megahertz as well. Basically whatever is possible from the ground-based instrument, because as we know, our atmosphere doesn't really allow a lot of low frequencies to penetrate. I mean, we can observe up to maybe 10 megahertz or maybe slightly lower than that, but beyond it, our atmosphere doesn't really is opaque to that. So at low frequency, we use this telescope called LOFAR, which is located in Europe. We work at various different telescopes. This is called LOFAR International Station. And the way we use it, that we point towards the zenith, near the zenith, and we track the source as it moves across the sky. So LOFAR has two different parts of antenna. LBA operates from 10 to 90 megahertz, and HBA, which is what these different tiles that you can see. It's hard for non-radio astronomer to imagine this is a radio telescope, but you may think it as like some wire from the ground, but they are in fact radio antenna. They are in fact radio telescopes. And they are actually studying the universe. And you can see them. We study basically a source. We track it as it moves past the zenith at both these frequencies. So we are actually in the process of conducting a survey called LOPS, where we cover the entire sky. So this is doing some kind of like a sky survey. The advantage we use for LOFAR is that LOFAR antennas are located at a very far, basically they are very far away from each other. So similar concept, like your multiple stations operating simultaneously, but rather than combining the signal like we do in an interferometer, we basically conduct the search independently. And then we barycenter the data. And then in the barycentric reference frame, we try and search if we see the same narrowband signal. Because since both these stations are like thousands of kilometers from each other, what happens is that when you see the signal, in the barycentric reference frame, they will be not at the same frequency, because as the Earth rotates, the line of sight velocity from both these stations are going to be slightly different. So you are going to see a slightly different frequency of your observation at both these stations. So you can use that to eliminate what is coming from terrestrial sources versus what is truly skybound. So I hope that probably gave you some flavor of what exactly we are trying to search, right? We are searching for all of these different kinds of signal. We have challenges of interferences, and we try to mitigate those challenges using various different techniques I outlined. With the last couple of slides, I just like to wrap up with kind of also highlighting how AI and ML is truly helping us push this limit. How AI is helping us, learn new ways of tackling these challenges. So there is another telescope that we use in our survey called the Parkes Radio Telescope, which is located in Australia. Parkes actually conducted the survey of the entire plane of the Milky Way, and we basically surveyed the entire Milky Way almost twice, and we collected something around more than 1,000 hours of data. So I have a PhD student who is working with me at Columbia University here, which I will be going after my current visit. And we basically carried out this entire survey of 1,000 hours, and we searched for different kinds of things. Now, due to interferences, large population of interferences, we got something around 300 million signals. Now, it is impossible for us to really, sort through 300 million hits, because obviously all of them are due to interference. So how do you get the needle out of these haystacks? And that's where AI is helping. Parkes is pretty good telescope. It can basically see multiple parts of the scale. It has 7 beam receiver. So even if we use the same strategy about seeing a signal is present in only one beam and not in the other, we still see a lot of signal. And that's a challenge. So this is where we use ML. So what we have done is that we have basically used a convolution neural network-based model to artificially generate signal, and then we have fed the signal into our data, and then we have trained the model to learn about the background. So what CNN has done is that the model has basically learned what exactly is the background looks like, what kind of typical radio environment we are seeing at the Parkes telescope. And we have created something around a few 100,000 examples of these artificial signal that we have injected. So now model is pretty well trained, and then we have applied the model on all of the data that we have collected so far, and we were able to detect almost 99.8% of the hit, although we have still end up with like a few thousands or a few tens of thousands, which we still have to deal with, but it's helped us eliminate quite a lot. And we did detect something quite interesting. So what I'm showing you in this plot, let me explain what you're seeing in this bottom plot. What you're seeing, this is an example of a 13 beam receiver from the Parkes. I misspoke. Parkes is a 13 beam receiver, not 7 beam. But what you're seeing here is that what we call waterfall plots. So for each plot, you can think of the x-axis as the frequency and y-axis as time. And these blips that you see in the middle, this is the example of a narrowband signal. And this is a real data, by the way, that we have seen a couple of examples of narrowband signal that are only present in 1 or 2 beams. It is possible for signal to be detected in more than 1 beam, by the way. If, for example, the source is located somewhere in the sky, that is somewhere in the middle of where both the beams are located. So you still have some spillover sensitivity between the beams. And if your source is located in that particular location, you will see the signal in both these beams. But it is impossible for signal to appear in the adjacent, not appear in the adjacent beam and appear in completely a far away beam. If we see a signal that is present in an adjacent beam, that is still valid, and we do have a lot of cases of that. We are trying in the process of eliminating them, trying to understand what frequency they are occurring. So the next step we are trying to do is that after we eliminate them being present in multiple beams, the next step is that we try and see if those frequencies where we see these signals are isolated, these frequencies are sort of very unique or not. And that's where we can search for, that's where we can eliminate a lot of them. Another thing that we tried with the ML, this was again published in Nature Astronomy 2 years ago, where we actually completely did the entire search using CNN. So traditionally, what do you do? Like what we did before, right? This is what traditionally we do. You create a label data, you simulate the data, you train your ML model like we did for the convolution neural network, and then you apply the model on your data. But in this work, what we did is slightly different. We basically use an autoencoder. So autoencoder is a consist of encoder as well as decoder. So you can train an autoencoder, you can fine tune the parameter in such a way that the autoencoder, what it does is that if you have label data, it learns sort of some of the basic attributes of that label data. And you can basically have certain number of parameter that represents the data, and every day new data that you can find, it can always fit into this multi-dimensional parameter space. So what we did with the autoencoder is that we created something around 15 different axes, 15 different parameter, and we train the autoencoder to reproduce. So the decoder basically reproduces the same signal as we fed to the encoder, and we make sure that it is doing the good job. Once the autoencoder learned these parameters very well, we use those parameters and then we train the neural network on those parameters. You may ask why. The reason for that is that if you use the traditional way, sometimes the traditional techniques are, you can think of CNN as some kind of like a black box. We are not necessarily sure always that the CNN has learned what it's supposed to learn. It could learn something that you don't really, you didn't really expected it to learn, and then it try to make prediction based on that. But with this, we can be assured that what it is learning is exactly what we want it to learn. It's like you're training like a student, for example. Like you give examples and you can say, okay, this is pictures of cats and these pictures of dogs, and like this is how you can disentangle them. So it's a slightly better way of doing it, and that's why it was a novel approach, and so we were able to publish this in Nature Astronomy. And we found a couple of good examples of signals that we didn't really anticipate. All of them we were able to rule out eventually, but again, a good example of what CNN or ML is able to do for us. All right, so I'll just wrap up with just last 2 slides. You may ask this question like, okay, we've been searching for radio signals for quite a while. What have we learned so far in the population of radio signals in the universe? Like, are we able to put any limits, or are we able to put any constraint on that? So for that, I'll just try to kind of draw your attention to this particular graph. What I'm plotting here, the x-axis is what we call the output power. EIRP stands for effective isotropic radiative power. And you can think of it as like, if you have a transmitter, what is the output power of the transmitter in volts? So that scale is in log scale. So you can think of it 10 to the power 5 is, for example, is the total output power of a Voyager spacecraft. And if you take an example of an aircraft radar, it is something of the order of 10 to the power 10. If you take an example of a planetary radar like Arecibo, that is broadcasting all the bright signal to detect planet objects in our solar system, that's pretty high. That's like 10 to the power 13 volts. And in fact, you can keep going higher and higher. For example, the Kardashev type 1 civilization, like if you take the entire energy that is possible for us to absorb on Earth coming from the sun, that is of the order of 10 to the power 17 or so. So that's the extremely high amount of energy. So these are different energy scales, just to give you an idea. Let's say you as a SETI astronomer conduct an experiment, you survey 1,000 stars, you don't find anything, but you were able to put a limit on 1,000 stars. So the y-axis is the transmitter rate, again in a log scale. So what it's showing you is that how many number of transmitters you are able to reject per star. So you can say there is less than 1 in 1,000 star that has transmitter on it, right? So if you survey 1,000 stars, you didn't find anything. So based on it, you can put limit like this. So you can say, okay, I was sensitive to detect Arecibo planetary radar kind of signal in 1,000 star. I did not find it. What does that mean? It means that there are less than 1 in 1,000 star producing Arecibo kind of signal, right? It's pretty straightforward. So if I combine all the SETI surveys that we've been doing so far, this is the limit we are able to place. All of the different surveys that people are doing, some surveys are sensitive to detecting basically detecting very high power transmitter in a large number of targets. Like if you do a sky survey, for example, not a deep one, but like a wide field survey, those surveys will be sensitive to large number of targets, but they will not be sensitive to very bright. They will not be sensitive to very weak signal. They'll be only sensitive to bright signal. And that's why you can see the slope there. So on this side, on the right-hand side, this is where you probably like look at the entire extragalactic object. You can look at like Andromeda galaxy, for example. You have billions of stars, but the transmitter needs to be extremely, extremely bright. And over here, for example, like this is like a solar neighborhood. So this is the limit that we are able to place. So we can sort of, in some sense, reject this particular parameter space that if ETI is out there producing electromagnetic waves, then it has to be in this particular area. We don't know the answer to that, but I always try to relate this problem same as, for example, people who are doing gravitational wave astronomy. I mean, gravitational wave observatories have been pushing the limit down and down every year, and then eventually you're able to meet the limit where you actually found the signature. I also feel the same way. Like right now, obviously we didn't detect anything, but in future, there are future telescopes that's coming online, like Square Kilometer Array, NGVLA. All of this, what it will do is it will push the limit further down and down. Like what ideally I would like to see is sensitivity of detecting like a planetary, like an aircraft radar kind of signal, like up to 10 to the power 10 volts of signal in the nearest 1 million stars. So I like to see something here, a survey that we can conduct somewhere here, right? This is -6, so like a 1 in a million star, and then it should have a transmitter. If it has a transmitter that's as powerful as like our aircraft radars or not. That would be a fascinating and exciting day. But so far, we haven't found anything, but I'm quite hopeful that the way we are currently conducting the search, the way the whole field has evolved over the year. Now, we are currently in a completely new domain which we have not explored before. We are searching for different varieties of signal which we have not really searched before. We are searching within radio telescope and other optical telescope that we have not really used before, and frequency band that we have not explored before. So the chances of us detecting is ever increasing, and that's all I like to add. And I'll thank you for your attention, and I take any questions if you have.
Awesome talk. So yeah, we have plenty of time for questions. So if anyone in the room or online wants to raise your hand, for the folks online, you can do that under the reactions on Zoom, or you can also post your questions in chat. Does anyone have any questions? Yeah, go for it.
Thank you very much. Very, very interesting. And I have a very naive question. But let's suppose you clone our solar system. And do you have any idea? So with all of our technology and everything that we emit, do you have an idea about the distance where we should put this solar system to be able to detect it with our technology?
Yeah. So it depends on what waveband or what signal you talk about. Let's take an example of like our atmospheric pollution that we have. For example, can ATI be able to detect? Answer is yes, but only up to a limited distance of like few tenths of, probably less than that, maybe a few tenths of light years, I guess.
Okay.
But if you take radio signal, now radio signals are great because they can travel much further out. And you take an example of, for example, Arecibo kind of planetary radar signals. If you have a same Arecibo dish on all the way to the other end of the galaxy, you can detect it.
Okay.
Right. So that just kind of broadens the entire parameter space. You take this argument around and you can say, okay, what are the chances of us detecting an ATI? If you do search in radio, you have a higher chance because they travel much further out. You don't require a lot of energy. They are very easy to produce. So to answer your question, yes, if you take the Earth technology that we currently exist, some of the bright signal that we produce has already traveled up to whatever distance, like 60, 70 light year that we have been producing them. But if the likelihood of them being detected by the same technology that we have right now is high, even at further out distances.
Okay.
Yeah.
Okay. Thank you.
You say we are detectable. Yes, we are certainly detectable. Even if we don't,
Good news.
we are not really trying to, we are not deliberately broadcasting, which is a good thing, right? I wouldn't really advocate for that, but something that we can't really escape, like a signal that is leaking out, we talk with our space with satellites, all of the radio communication is already being sort of getting out. So they are really leaking into space. So there is a way for, I mean, they are basically traveling right now.
So may I push back a little bit on, we shouldn't be transmitting, because even if we don't transmit, they can actually see us through the spectral signatures of the Earth or something. They can make it.
City lights.
Yeah, they can make a big telescope and look at the Earth and take an image of the Earth, just like we are trying to do with to find other Earths, right? So, I try to equate it as a a kid trying to hide by closing their eyes. So even if you shut down all the radio, we are still discoverable because we still have technology on the time.
Right.
So we will be discovered no matter what. So,
Okay.
The reason why I said I would advocate for transmission is because it's very hard for all of us to agree on what to transmit. Like, would it US who would make the decision? Okay, because you are speaking for whole Earth, right? Like, what exactly you want to transmit? That decision, I guess, that we as an entire species needs to make, not like one nation or one entity. So it's a hard problem. So I don't think so. One person or one entity should do that.
So I have a question for you. I might have missed it earlier in your talk, but kind of like the same questions, like what's the ideal distance to put our solar system? But what's the ideal star to look at? Because there's a lot of conversation about, the habitable zone around M-type stars versus solar type stars, but M-type stars do a lot of flaring, so
Yeah.
that's gonna be.
Well, I mean, let me go back to the
Yeah, sorry,
sources.
you talked about this already.
Yeah. Well, I didn't go into much detail on that, but our 1 million nearby star sample basically are a bit agnostic in that regards. Like, we don't really focus only on the habitable sort of zone planets, because we all know that our searches are sort of heavily biased towards our search technique and our sensitivity. And just like the estimate we make on the population of extrasolar planet is based on what we have found, right? Like, we don't say that, okay, only these stars have planets around it,
Right.
because we found it. Our estimates are that because we found them, that means other stars will also have planets around it, right? So I wouldn't really kind of go only for the planets or only for the stars which we have found the exoplanets on. We try and basically be agnostic in that. We try and search almost all spectral type stars. In fact, the 1 million star sample, we even have a smaller sample of 2,000 stars, what we did is that we took an HR diagram and we took basically 100 stars from each spectral type category, including the giant branch star as well. So we are not really keeping anything out. We are looking almost on all kinds of stars.
Right.
Okay.
Nearby stars dominated by M-dots.
So this sample might probably be dominated by MGOT, because we try, as I said, we try and search for them as if they are close to us. We want to basically look at them.
Thank you.
The signals you're searching are very short duration, or can you search for long duration?
Could you repeat?
Yeah, so I think the question is, what is the repeatability of our detection, or what is the repeatability of the signal that we are trying to detect,
Yeah,
right?
is it millisecond time scale?
They are typically pretty, I mean, we expect that signal to be sort of persistently on. That's one of the criteria for us. If a signal, so there are two kinds of signal, like signal that are broadband can be just on for a millisecond or less than that, because we search for like microsecond duration artificially dispersed signals, which can last for microsecond. And if you go to the optical domain, then we are searching for nanosecond duration. But when you talk about like narrowband signal that are highly focused in sort of single frequency, we would expect them to be last longer than at least our observation span. If they are lasting less than the amount of time than the length of our observation, we have no way of like isolating them from interference. So we are sensitive only if they have a high duty cycle. So that's one of the constraints we have. I mean, I only talked about two axes, like the sensitivity versus the transmitter rate, but there is a third axis, which is the repeatability or duty cycle of the signal. Okay. So we are not really covering things which are very low duty cycle. That's impossible for us, unfortunately, at this point.
Is it the sensitivity or a computational?
Sky coverage.
Okay.
So you need all sky all the time kind of surveys.
Okay.
Instrument that can look at all the sky all the time, like FRBs, for example. If you think of the FRB with an extremely low rate, like 1 in a million year, right?
Yeah.
What do you do with that? Like, or 1 in 1,000 year, for example, you need to look at all this kind of all the time in order for you to catch one. So something similar for us as well, like if you, something is this extremely low duty cycle, then unless you have an sort of all the time monitor, you will not find it.
If you could briefly go back to the Dyson sphere, you had a class time for transits. And that's great for a rigid Dyson sphere, but a rigid sphere
Yeah, I
is going to be
understand.
unstable, and the sort of canonical form is actually a swarm of orbiting collectors, which would, I think, be considerably less detectable just because it's more stochastic.
Yeah, that's totally true. We expected to kind of have significant signal to noise ratio in our lighthouse. And we are definitely constrained by that. Yeah.
We do have transit signals for these individual Dyson sphere.
Yes, so we simulated different shapes, and what CNN does is that it learns that, okay, if the shape, if it is a blob on this particular side, which means that it will produce this kind of light curve. So once we try, we have the model also applied on unseen shapes. So we actually also give transit light curve of an that the model has not seen before, and it is still able to predict the shape based on what it has seen before. That okay, likely that you will have some blobs here and some blobs here, which is what is causing the shape that you are seeing right now. Based on all the examples of, I mean, this is just the 3 examples. We have hundreds and thousands of examples that we created of different shapes on transit lighthouse.
And on the simulation on the right, do you also take into account the reflecting light during the simulation?
No, not on this, but yeah, that's a good point. That could be a reflecting light as well when this thing goes on the backside. Yes.
Okay.
I was talking to Ravi about this, about like maybe you can use polarimetry because artificial surfaces create reflected light in a different way than a natural object. So you can use polarimetry to detect artificially reflected lights.
Awesome. Any last questions? Anyone online want to ask anything to our speaker before we close out?
I saw some question on chat, but
I think it was just for me. I was
Okay.
posting some things, but yeah, people are saying great talk. Yes, let's thank our speaker one last time. And I think you're still around today.
Yes.
If folks want to meet with you. So just get in touch with me or Robbie and we can put you in contact. Thanks everyone for coming out. There's a lot of folks that are new here. So I put my email in chat. We do these exoplanet seminars pretty regularly. We have 2 next week actually. So if you're interested in these, definitely get in touch with me. But thanks a lot. I'll end the meeting now.